Hi, I'm Kritan Bhandari, working with Sean and Dr. Wang at AirLab CMU. This is MAC-VWO. The main idea is that when you fuse a camera with wheel encoders, the hard part isn't the fusion, it's deciding how much to trust each sensor. We try to solve that by putting uncertainties from both sensors in the same physical unit. One of the questions might be why use both sensors at all? Stereo VO assumes the scene is textured, well lit, and still. When a vehicle is traveling in degraded scenarios with low light, motion blur, visual odometry struggles. The failure is detrimental because a few confidently wrong matches biases the motion estimate, and because VO integrates, the bias never washes out. On the other hand, light and texture don't affect wheel encoders, and they are inherently metric, but they measure wheel rotation, not vehicle motion, so slip and radius error accumulate without bound. The important part is that these failures are independent. The tunnel that blinds the camera does nothing to the wheel, so fusion should work. So why isn't this solved already? Classical estimators do fuse these sensors, but they give each a fixed noise covariance, tuned per platform and held constant throughout. The problem is that reliability isn't constant. Vision swings by orders of magnitude between a textured intersection and a blank tunnel wall. Encoders are near exact on a straight stretch and badly wrong through one slipping kernel. The fixed weight is therefore not robust most of the time. Learning based odometry does predict per frame uncertainty in recent approaches, but it comes out in pixels or photometric residuals, none of which share a scale with an encoder's physical noise. So the open question is how much can a system trust each sensor per frame and real physical units? MAC-VWO prior work from our lab tries to solve the problem for stereo cameras. MAC-VWO predicts key point uncertainty directly in metric 3D space. A shared network estimates depth, flow, and the uncertainty of both. Those project into a full covariance per key point, and critically, that covariance is in meters, not pixels. Once one sensor reports in physical units, we don't need a conversion factor. We just need the second sensor to report in the same unit. Fusion stops being a tuning problem and becomes inverse covariance weighting. So here's our approach. The top branch is MAC-VO, inherited unchanged, a stereo pair, a shared matching network, metric 3D covariance, and each key point enters the optimizer as a point-to-point factor. The bottom branch is our contribution. We pre-integrate the encoder stream between camera frames under a differential drive model, then propagate its noise through the linearized dynamics, giving a relative pose covariance in meters and radians. Both meet in a two-frame pose graph, each factor weighed by its own inverse covariance. Because both are in the same units, nothing in that weight matrix mediates between the sensors. There is no balancing parameter. Briefly, this is what the wheel model actually looks like. Standard differential drive. Forward velocity is the mean of the two wheel speeds, and AR rate, their difference over the track width, integrated at the midpoint heading. Variance scales with distance traveled because slip and radius error starts adding per wheel revolution. A vehicle stopped at a red light accumulates no encoder uncertainty, and current modeling captures that nuance. We use a first order error propagation strategies that carries it forward and get a covariance in meters and radians which is directly comparable to the visual one. We evaluated on the Irwin 39 sequence of KAIST complex Irwin dataset. Wheel-only dead reckoning drifts to about 45 meters of trajectory error. Stereo-only MAC-VO gets 13.4 meters. Fusing gets them to 8.9 meters, 34% better than stereo alone, roughly 5 times better than wheels alone. And the reason follows what each sensors observe. Over a certain interval, the encoders measure distance directly, while vision has to triangulate it. So wherever depth is poorly constrained, the weighting shifts towards the wheel automatically, per frame with nothing tuned. The trajectories tell the same story. Dotted is the reference, solid is each estimate. As you can see, wheel only departs early and never recovers. Stereo only follows the route closely at the start but begins drifting at the first turn. The fuse estimate has the tightest fit at the first turn and throughout the rest of the trajectory. So the main takeaway is put uncertainty in physical units and fusion becomes principal inverse covariance weighting instead of parameter tuning. The next steps are learning the wheel covariance per frame instead of fixing it per platform, a learned motion model for drivetrains the analytical model can't describe, and bundle adjustment in the backend. Thank you, and thanks to Denso and to Dr. Wang, Rachel, John, and Isan for all the help.